Hi everybody, this is Merlijn van Veen from the Netherlands in what is hopefully a one-take attempt at trying to explain the subwoofer align calculator. I've been getting a lot of requests lately from people over email and social media if I could enlighten a little bit the functionality and the features and the purpose of the sub-align calculator. So let's give it a try. Um, I wrote the subalign calculator because, like most of my calculators, I was looking for a way to make these abstract concepts like phase and phase offset and phase shift tangible. And like most of you, I'm graphically inclined, so show me a good picture, and it will mean more to me than 1,000 words. So, what is the issue with subwoofer to main speaker alignment? Typically, it has to do with the physical displacement between the sources and the fact that we, as an audience, within the audience plane, aren't capable of maintaining our equidistance to those sources. We're not equitemporal 9 out of 10 times to, in this instance, the main array and the subwoofers. The main array in this example is a line array, and it suffices to choose the geometrical center between the extremes of the line array, which is for all intents and purposes the point of origin, the acoustic center for the low frequency energy. But it could also just as well be a point and shoot speaker, like a simple two-way enclosure or a three-way enclosure. The principle is the same. So when you fire up the calculator, then the default uh, the default settings will be as shown in this screen. Room temperature in the top left corner is currently 21 degrees, and we get to position our subwoofer speaker, which is currently sitting on the floor at a distance of 0 meters and an elevation or altitude of 0 meters. The main speakers, on the other hand, are sitting at 0 meters distance and an altitude or height of 10 meters. So in the vertical plane, there is a vertical displacement of 10 meters, and this is what causes the issues to begin with. Um, our virtual audience plane starts currently at 5 meters distance. We have a standing audience with ear height of 1.8 meters, and this audience stops at 60 meters distance. And as you can see from the values in this section of the calculator, it is a flat audience, and there's no elevation, there's no inclination in the audience plane currently. Um, in the SPL plots section, we get to choose the frequency we're looking at, and currently that is 125 hertz. Um, I strongly recommend always um, to look at frequencies which is 1/3 octave above the actual crossover frequency. In this case, we will do an example with a crossover frequency of 100 hertz, and 1/3 octave up from there is evidently 125 hertz. But if you're doing a 80 hertz scenario, you will want to look at 100 hertz instead. And if you're doing a 63 hertz crossover between your main and subwoofers, you will want to look at 80 hertz instead. In a bit, I will elaborate why this is. Um, the alignment section in the bottom left corner I will leave for now, because first I want to explain the charts to the right of the setting that we're seeing. The phase offset chart in the top left basically shows you the alignment position and the degree of error that will be introduced when we move to the front or to the back of that alignment position. So it shows you the relative phase offset expressed in degrees. Um, the SPL plot shows you the combined output for set position. Uh, depending on the phase offset. The red trace is the combined output of the main speaker and the subwoofer together. The green line is the level over distance of, in this case, the subwoofer. It has a corresponding color to its settings in the top left corner. The blue trace is the level over distance for the main speakers, and that we currently observe a difference in the start of the audience, a relative level difference in the start of the audience, is because the subwoofers are sitting on the floor, they're ground stacked, and the main speakers are flown at a height of 10 meters, and that explains this initial level difference in the front of the audience. But if we move to the back of the audience, we can see that this vertical displacement becomes negligible and the levels start to approach each other. The reason why we see a big cancellation over here is shown in the top chart, the phase offset chart. We can see we have cancellation at 30 meters distance because we have an offset of 180 degrees. Now what does that mean in terms of phase? Well, you have your phase wheel in the bottom left corner, and as you can see, with 180 degrees of phase offset, we are at the bottom of the phase wheel and we have cancellation. So top left chart shows you relative phase offset, bottom left chart shows you sound pressure level or output over distance. And the whole purpose of this calculator is to attempt to put as many people, as many spectators in our audience within that top section of the phase wheel, with phase offsets of 0 to 120 degrees in one direction or 0 to minus 120 degrees in the other direction. That is the positive side of the phase wheel, where we can expect summation of as little as 0 dB, nothing gained, nothing lost, with 120 degrees phase offset on either side, to as much as 6 dBs with 0 degrees phase offset, where we will have maximum summation. So it's about getting as many people simultaneously within the top of that phase wheel. This is the difference between coupled and uncoupled. If we go beyond 120 degrees in either direction, we become uncoupled and we start to see losses. So trying to get as many people within the top of that phase wheel. The center top chart, called SPL plane, that is plane and not plan, shows us the sound pressure within the audience plane. And I emphasize plane because this is not a plan view as in the drawing plan seen from above. No, this is the actual sound pressure within the plane. So if there's an inclination in the audience area, if there's an elevation in the audience area, it will show us what goes on within the plane of the audience at ear height. This is not a plan view. In contrast to the SPL section view, this shows us the SPL over distance seen from the side. This is the section view. So that explains those two charts. Then there are two more charts that we need to discuss, and this is the center chart in the bottom, which shows you the relative level difference, again in the plane view, not plan view, but in the plane view within the audience plane. And to the right of it, we have the relative level difference section view as seen from the side. And it uses three distinct different colors, which are green, isolation, yellow, transition, or transition, or red, the combing zone. These colors correlate to Bob McCarthy's summation zones. Now, for those who do not know what summation zones are, it's beyond the scope of this video to explain that in great detail, and I strongly encourage you to read the chapter Summation in Bob's book. Now, that is page 60 for the first edition, page 61 and on for the second edition, and those who have a copy of the third edition can find the summation chapter starting at page 125. And the whole summation zone idea basically tells us what we can expect in terms of the extent or scope of the comb filter over level variance. So when we are in the combing zone, depending on the relative phase offset, we can expect combing with an extent or scope, the ripple, the difference between the peaks and the cancellations, of 12 decibels or more. However, when we have relative level differences in excess of 10 decibels, we are in what is called the isolation zone, and the ripple has been reduced to 6 decibels or less. The area in between with relative level offsets between 5 and 10 decibels is called the transition zone. And this is where we can expect frequency response ripple in order of 6 to 12 decibels. So basically, these three zones tell us the amount of trouble we can expect. Again, this is beyond the scope of this video, so I strongly encourage you to read chapter Summation in Bob's book, and here are the respective page numbers. But besides these distinct colors, green, yellow, and red, you can see that I've added a checker pattern, a checkboard pattern on top of it. And this is basically the area where we want most of our audience to reside. It's the combing zone, the checkered part of the combing zone, where we are within the top of the phase wheel. The top of the phase wheel where we are coupled with with phase offsets of 120 degrees or less in either direction. And here you can see it in the plane view. This is not the plan view, but the plane view. And here you can see it in the section view as seen from the side. And it resembles a searchlight, if you will. So that pretty much explains every chart we can see here. Now, remember that I said that instead of looking at the actual crossover frequency, it makes sense to look 1/3 octave up from there, because it is not a single frequency that we're trying to get time aligned. No, actually, there's a whole span of frequencies that we are trying to get time aligned, not just the actual crossover. The crossover is where we are in the combing zone, and it's of the utmost important that we are in time, because then we will have the most amount of summation, and if we're not in time, we will have the most amount of cancellation. But it doesn't stop there. The whole area where our levels are within 10 decibels is the frequency span where we need to be time aligned. Only beyond that frequency span does relative level differences in excess of 10 decibel put us in the isolation zone where time no longer matters. So it's not just the crossover frequency where we need to be time aligned. No, it also matters 1/3 octave up and down of the crossover frequency. We need to be time aligned throughout an octave wide frequency span for a typical fourth order crossover. Because if we're not time aligned for that range of frequencies, we risk frequency response ripple throughout the crossover area. Ripple which manifests itself to the left and the right, or even at the actual crossover frequency itself, throughout the crossover range. For more information regarding these phenomena, I encourage you to watch the video on my YouTube channel, which is called Matched Slopes. So it's just not important to be phase aligned at the actual crossover frequency. No, we need to be phase aligned, time aligned throughout an octave wide span for a typical fourth order crossover. And that is why I recommend you to look up to look at a frequency 1/3 octave up of the actual crossover frequency and not the crossover frequency itself. And like I said before, for a 100 Hz crossover, that will be 125. For the 80 Hz crossover, that will be 80. Will be the crossover frequency, so you need to look at 100 Hz. And for 63 Hz crossover, you would need to look at 80 Hz instead. That is my recommendation. So this brings us to the section of the calculator which is called the alignment part. And currently it shows us that our geometrical problem, which is this story, the fact that we cannot maintain our equidistance to the sources, the scope of that problem expressed in time, because as you can see these triangles do not have their legs do not have the same length, and the scope of this problem currently for 125 Hertz expressed in phase, that is a 492-degree problem that we somehow need to divide throughout our audience area, because the phase wheel tells us we only have a 240-degree window of opportunity to be actually coupled. And because the phase span value exceeds that 240-degree window of opportunity, chances are that we do not get to put everyone in our audience within that coupled part, that coupled area. And that is the consequence of the physical displacement between those sources. If there were no physical displacement between the main speakers and the subwoofers, then there would be no issue at all, because both systems are co-located in space and there would be no phase offset throughout the audience areas. This is one of the arguments in favor of flown subwoofers, because it's the physical displacement in the vertical that allows us, that introduces the trouble to begin with. So right now, for 125 Hertz, under these conditions, we are dealing with a 492-degree problem. And if we reduce the frequency, if we go to the actual crossover frequency, we will see that the scope of our problem has been reduced to about 390 degrees. So this is caused because we are dealing with longer wavelengths and longer periods. So the same amount of physical displacement allows us more wiggle room, if you will, at a lower frequency. If we go 1/3 octave down, then we can see that the scope of our problem has been reduced to 350 degrees. And if we go even lower to 63, then the same geometrical challenge has been reduced to a 250-degree problem, and this is reflected in the checkered pattern in the relative difference plots. We can see that more and more people are now coupled because we are reducing the amount of issues when we go down in frequency. However, if we go back to our original frequency of 125 Hertz, we can see that the scope of our problem is bigger, 492 degrees to be exact, and we only have a 240-degree window of opportunity, which is currently based on this alignment position, which is currently this part of the audience as shown in the checkered combing zone part of these two graphics, the relative level difference, plane view, and section view. It's the same story seen in two different dimensions. And as we can see, these are not a lot of people in comparison to the entire audience areas. This would constitute a minority. And that is because our alignment position currently is too close to give any meaningful results. Our alignment position is currently at 10 meters. And this will be the position if you ask the calculator to split the difference. Now, what does it do, split the difference? It will look at the entire scope of our problem, which is currently 492 degrees, and it will try to find an alignment position where the error in the front of the audience is proportional to the error in the back of the audience. So in other words, at the start of our audience area at 5 meters distance, as shown in the audience plane settings, currently at this position, the subwoofers are physically closer and leading by approximately 245 degrees. And in the back of our audience, at 60 meters distance, the subwoofers are lagging by the same amount, half of the phase span value, 245 degrees. So that is why that button, which executes a macro, is called split the difference. However, I always have been taught that you should do the alignment in the back of the venue. Um, so how do we manipulate that position and make it appear in the back of the value? That's done by entering a offset value. So if we enter in this yellow box minus 492 degrees, which is currently the scope of our problem, and we press the button split the difference again, we will see that the alignment position has now moved to the rear of the audience for 125 Hertz. And now we can see that a big portion of our audience resides within the checkered area of the relative level difference plots, as seen in plane view, but also seen in section view. And it resembles kind of a searchlight in the section view, if you will. So right now we're looking at the outcome when we do the alignment in the back of the audience. Okay, so what is the advantage of this position? Well, it's shown in the SPL chart over here. Right now we can see that the combined output of the main speaker and the subwoofer drop at an identical rate as the individual systems. So the subwoofers, they go down in level, and the main speakers go down in level at the same rate. But so does the combined output, as you can see. The slopes of these charts, of these lines, the slopes are virtually identical, and that means that the tonality of the system stays the same because they move in parallel, if you will. So what will happen then if we move to the front, if we change our alignment position from the back of the venue and move towards a different location, most likely the front of house position? Well, we can exactly determine the position to have a predetermined phase offset left over in the back of the venue. So it sounds difficult, but once you get the hang of it, it's more easy. So what if we want to move so much forward by a yet to determine amount? If we want to move a certain amount forward and reduce the phase offset in the back to a difference of only 90 degrees. Because right now the difference in the back is 0 degrees, but we want to move more forward, more towards the front of house position, and not go any further, so that the offset in the back will become 90 degrees or less. Well, then we need to manipulate the offset value, and the way to do that is to add to the current value twice the amount of offset you want to be left over with in the back of the audience. So if we want to be left over with 90-degree phase offset in the back of the audience, we need to add in the formula in this specific cell, we need to add an extra 180 degrees and press enter. And then we need to split the difference, and it will move the alignment position to the front and leave us with 90 degrees phase offset in the back of the venue. And it shows that we now have a broader range, a larger checkered pattern, if you will, a larger part of the audience that is seeing a coupled interaction between the main speaker and the subwoofer. But because of the 90-degree offset we now have in the back over the previous 0-degree offset we had in the other example, we only see 3 dB summation, because in the back of the audience we are no longer at the top of the phase wheel as shown in the bottom left corner, but we are now at 90 degrees and we have lost 3 dB of summation. We still have 3 dB of summation, but we lost 3 dB over what we could have obtained with no phase offset. In exchange for that, we have now catered a larger portion of our audience with coupled sound, um, which is the upside of this particular alignment position. However, the downside is, if any, the downside is that if we look at the slopes of the combined output, the red trace, in comparison to the individual systems, we can see that the slopes, the loss rate over distance, they are no longer parallel. And this means that our tonality will be affected by choosing this particular alignment position. So we get to cater more of our audience. We get to cater them coupled sound, if you will, in exchange for 3 dB tonal variance, because the individual systems drop at the same rate over distance, but the combined output at the crossover frequency drops at a higher rate. And that is the trade-off. So if you want to cater more of your audience with coupled sound, then the price you end up paying for that is tonal variance. That being said, for this particular example, this would be still a very acceptable solution. Now, what if we want to move so far to the front that the phase offset in the back of the audience will be limited to 120 degrees, putting us at the edge of what is called coupled, putting us at 120 degrees phase offset, and then we start to see losses. Then we have to take our initial value, the negative amount of phase span, or the scope of our issue, scope of our problem, and add twice the amount of phase offset that we want to be left over with in the back of the audience. In this case, 120 degrees, so we need to add 240 degrees, enter and split the difference. And what was previously 90 degrees will now be 120 degrees. And this is, in my opinion, how the extent or how far we can push the envelope. Because by now we will have a situation in the back of the audience where we have nothing lost, nothing gained. We are at the edge of the positive side of the phase wheel. We are at the edge of the coupling zone, if you will. And if we go any further to the front, we will start to see actual losses in the rear of the audience area. You could argue that we even catered we enveloped a larger part of the audience within the checkered portion of the relative level difference chart. But what is also very apparent is that the slopes, the tangents, the loss rate over distance, these lines are no longer parallel. And this means that even though we are coupled, we will experience a 6 dB tonal difference throughout the crossover range when we move from the front to the back of the audience. So this would be, in my opinion, the maximum amount we can move forward before we start becoming uncoupled in the back. Because if we say, okay, let's end up with 150 degrees phase offset in the back, then we need to add twice that amount to the phase span value. So that will become 2 times 150 is 300 degrees. Split the difference. And what was previously 120 has now become 150. And 150 puts us over here at the orange to red transition on the phase wheel, and we have lost 6 decibels in the back of the audience. Clearly something that we do not want to introduce, something that we do not want to achieve, not to mention that the coupled portion of our audience has now become less than before. So moving so much to the front, up to the point where we see phase offset in the back of the audience in excess of 120 degrees, is not advised. Um, so let me go through it step by step once again. Let's start with the alignment position in the back. And for this we need an offset that is equal to the negative value, the negative amount of phase span that we see in the cell above it. Split the difference. And this will move the searchlight, the coupled searchlight, as I've come to call it. It will put it back in the rear end of the audience. And funny enough is that this portion where we are coupled is being reflected in the SPL section view. This lobe, this central lobe, this is the lobe where we are on top of the phase wheel. This is where we want our audience, or the majority of our audience, to reside. And by moving that alignment position further to the front, we will see this searchlight of coupled sound, of coupled combined output of both subwoofer and main speakers. We will see that searchlight move, tilt down, if you will, scan the surface, scan the audience from back to front. So let's start with a leftover phase offset in the back of the audience of only 60 degrees. If I now press split the difference, then we will see the alignment position move to the front and the searchlight, the coupled searchlight, tilted down slightly. But this is still a very acceptable solution, and it probably puts us somewhere around front of house. So let's introduce a larger offset in the back of the audience of maybe 90 degrees instead of 60. And we will see that the searchlight goes even down further, and so does that central lobe in the SPL section, because we are left with 90 degrees phase offset in the back. So let's go to 120 degrees phase offset in the back, and we will see that searchlight tilt down even further. And this is, for this particular example, this would be, in my opinion, the furthest forward position before we start to become uncoupled in the back of the audience. That being said, let's push that position even further to the front, knowing the outcome, knowing the risk. And we can see that the searchlight tilts down even further. So let's really push the envelope. Let's go even further to the front with our alignment position. And we can see that searchlight scan the area from back to front, going down, down, more tilt, more tilt. And we end up covering less of our audience with coupled sound, if you will. So that basically shows you the trade-off between aligning in the back, where you get to cater, where you still get to cater a majority of your audience with coupled sound, but where you also have the biggest audience area where your tonality stays the same, because the slopes, the loss rate over distance of the individual systems is parallel to the combined output. However, should we decide to move to the front, we get to cover maybe a larger portion of the audience in exchange for some tonal variance. This would still be a perfectly acceptable solution. Only if we really push that envelope and go so much forward that we are left with 120 degrees in the back, then we do not gain a lot of more people within our coupled area, but we do get 6 dB of tonal variance, and that is a trade-off. So it's basically a trade-off between uniformity, tonal variance, level variance, versus how much people will I be able to collect within my searchlight, within my coupled searchlight, which is very apparent in the relative level difference section. And the funny thing is that if we go for the arguably best solution, which is in the back of the venue, if we are aligned, time aligned for those frequencies, which is currently 1/3 octave up from the crossover frequency, then we will be definitely time aligned at the actual crossover frequency, and we can see that the checkered area has even increased slightly because of the reduced problem that we're facing. What was previously a 490-degree problem at 125 Hz has now only become a 390-degree problem at 100 Hz. And if we lower even in frequency to 80 Hz, then surely we are still aligned, still coupled, and we cover even more people because we're dealing with longer wavelengths and longer periods. So there you have it. That pretty much shows you what you can expect in this instance for a flat audience area when the main speaker and the subwoofer are physically displaced by 10 meters. Um, and to bring the point home, if we go back to our 1/3 octave up of the intended crossover frequency, um, if I move the subwoofers, if I co-locate the subwoofers with the main speaker and put them also at a 10-meter height, then there is no longer a phase span. The scope of our issue, the scope of our geometrical problem, which is the cause for the incapability to maintain our equidistance, has been reduced to 0 degrees. And you can see that now the checkered part, the coupled part, covers anyone and everywhere in both the plane view and the section view. And this is the reason why this is one of the arguments in favor of the of flown subwoofers. Now, what if we want to combine flown subwoofers with ground stack subwoofers, which is not uncommon in large-scale events? Well, then we have to think of our main speakers as flown subwoofers, and our original subwoofer will become our ground stacked subwoofer. So, back to the previous situation, um, just think of our main speakers at 10 meters height. Think of them as your flown subwoofers, and our previous subwoofer will become the ground stack subwoofer. And 9 out of 10 times, these two subwoofer systems, the flown ones and the stacked ones, share custody in the 63 Hz, 32 Hz frequency range, in the infrasub range, if you will. And if we change that frequency to 63 Hz, then the scope of our problem, even though our subwoofer systems are displaced by 10 meters in the vertical, is reduced to a 250 degree problem. And we have a window of opportunity of 240 degrees. So those figures virtually match. And if we stick to our duty alignment in the back of the venue recommendation, then we can see that even though there's 10 meters of physical displacement between our ground stacked subwoofers and our flown subwoofers, that the majority of the audience is very much in the coupled area, the area where we reside in the top of the phase wheel. And needless to say that if we are time aligned or coupled for 63 Hz, where we observe a 250 degree problem, then the same will be definitely true when we lower that frequency by 1 octave, because by the time we get to 32 Hz, that geometrical problem will be reduced to a 126 degree error for 32 Hz. And as the charts show, we are still, everyone is still very much within within the coupled part of the combined output. And if you think about it, it all makes sense. We're dealing with such long periods, such large wavelengths that we can suffer, we can tolerate, we can get away with quite amount of vertical displacement, which is 10 meters as we speak, and still get the majority of our audience within the top of that phase wheel. So as far as I'm concerned, that pretty much concludes this video Should you have any questions, you know how to contact me over social media. Send me a private message or email me at info@merlinvanveen.nl. Thank you for your time and see you in the next video.